Welcome students, welcome to the lecture series on digital electronics. It is a subject in third semester, Diploma ETCE. The course code is ETCE/DE/S3. Today we are in lecture number 19. I am Paulus Tridhar, the course coordinator and assistant professor in Department of ECE, Guru Nanak Institute of Technology. Now let us start lecture number 19. Now going through the course objectives. Now our subject digital electronics, it consists of 60 number of total lectures and the credit is 4 credit subject. Now we are in unit number 3 or module number 3, that is combination logic circuits. In unit 3 there are 4 subunits. First one is 3.1 arithmetic circuits, 3.2 design of circuits using universal gates, 3.3 code converters, encoders, decoders, multiplexer and demultiplexer, and unit 3.4 parity generator, checker and comparator. Now we are in unit 3.1. We will be starting this unit 3.1, that is arithmetic circuits. It consists of half adder, full adder, half subtractor, full subtractor, parallel and serial full adders. 1 is complement, 2 is complement and 9 is complement addition. Now let us go through the course objectives, which are very important in the study of a course. Now this is the first course objective, that is do conversion of the number systems. Second is understand the concept of the logic gates and its operation. Third is design simple logic circuits using logic gates. 4 is design of combinational circuit. 5 is design of sequential circuit. 6 is gain the comprehensive ideas on various memory devices. 7 is understand digital to analog and analog to digital conversion techniques. 8 is understand different logic families and their comparison. Now these course objectives are very important in regard that the student after the completion of the course will be able to see that all the course objectives he is able to understand all this course objective. That is, he is able to design the number systems, then logic gates. He can design the digital circuits as a whole, and he can also apply digital electronics in other applications of the electronics field. Now there's 4 number course objectives, that is the design of the combination circuit is a very important course objective for this unit 3 and also for subunit 3.1, that is arithmetic circuits. So our lecture number 19, this will correspond to the course objective 4, that is design of the combinational circuit. Now let us move forward to lecture number 19. Now this is a short lesson plan of our lecture number 19, which is of unit 3, that is the arithmetic logic circuits, and we will go through the subunit unit 3.1, that is the arithmetic circuits, half adder, full adder, half subtractor and full subtractor. Here in today's lecture we will be learning this few topics. The first topic is we will be having an overview of the combination logic circuits. That is, what is a combinational logic circuits and what is a sequential logic circuits. That is the types of the logic circuits we will be studying. Next is the half adder. In the half adder we will be studying about all the truth table, then logic diagrams, block diagrams. Then in full adder we will be studying the general expressions of the sum and the carry, and also full adder using 2 half adders. See, this full adder, that is a general expression, and also using the 2 half adders are very important for your semester exams also. So this lecture is very important in regards for your SEM questions and also the answers. We will be discussing the half adder, full adder using 2 half adders. All these are very important for your semester exams. So Before starting the lecture number 19, let us have a quick recap of the previous lectures. So in the first lecture, we have studied about the difference between the analog circuits and the digital circuits. And next we have studied about the digital logics, that is the applications of the digital logic in the different fields of the electronics. That is how it can be used in communication fields like this. Next is we have studied about the number systems and also the conversions of one number system to the other. Next we have studied about the basic gates, universal gates, XOR gates, all the types of gates which we will be requiring for designing the logic circuits or all the digital circuits, which we will be also here also in half adder. The chapter we are going to study, we will be using an XOR gate, AND gate. So this we had already studied in the previous lecture. So we can see how the applications of the basic gates or the gates are going on in the later chapters. Next is we have studied about the minimization techniques, that is the Boolean algebra, K-map, all these techniques we have studied. In the Boolean algebra, we have studied about the different proofs, De Morgan theorem, all these are very important for the minimization techniques. Boolean algebra is a one type of minimization technique. But now what happens, Boolean algebra is a quite complex one. We also don't know which expression will be having the right expression, that is, it is not suitable in some cases. So we are using the K-map. Now K-map, we have studied about the 2 variable K-map, 3 variable K-map, 4 variable K-map, and also the don't care combinations. We have seen that the don't care combinations also play a very important part in the digital circuits. That is also in case of the minimization techniques. So next we will be starting the combination logic circuits, or that is the overview of the combination logic circuits. So let us start the combination logic circuits. Now what happens, a combination logic circuit, before starting it we need to know a digital system. Now digital system is basically of two types. First one is the combination logic circuit and second one is the sequential logic circuit. Now when these two circuits come to our mind, another thing should come to our mind, that is, what are these two circuits? Why these two circuits are called combination logic circuit, another one is a sequential logic circuits. For understanding this, we need to know what is the combinational logic circuits. In a combinational logic circuit, the output at any time depends only on the input values at that time. That is, suppose at time t, some inputs are going and also we are getting some outputs based on the inputs. So that at that time t, the outputs will be dependent only on that input values. But what happens in a sequential circuit? In a sequential circuit, the output at any time depends on the present input values as well as on the past output values. So this one is a little different from the combinational circuit. In the combinational circuit, the output only dependent on the input values. But here in sequential circuit, the output depends on the present input values and also on the past output values. So in the sequential circuit, we need some memory element. Why? Because to remember the past output values and also some feedback elements. See, in the later chapters, we will be having a detailed study of the differences between the combinational circuit and the sequential circuit. That is, why it is called combination circuit and why the other circuit is known as a sequential circuit. So, but for our understanding of the other circuits also, we need to know the differences here. So I am giving you a brief study of these two circuits. Now the examples of the combination circuits are adders, the half adder, full adder, all these adders are examples of the combination circuit. And the examples of the sequential circuits are flip-flop, registers, then counters. All these are the examples of the sequential circuits, and this we will be studying in the later chapters. In module 4, 5, we will be studying all the sequential circuits. But in module 3, that is the combination logic circuit, we will be studying about all the combination circuits. that is the multiplexer, decoder, encoder, like this, where the output at that time depends only on the input values. So next is we need to know the procedure for the design of the combinational circuit. Now, any combinational circuit can be designed by following the design procedure as follows. First one is, from the description of the problem, identify the inputs and the outputs and draw a block diagram. Next is, draw the truth table such that it completely describes the operation of the circuit for different combinations of the inputs. Third one is, write down the switching expressions for the outputs. Fourth one is, simplify the switching expression using either algebraic or K-map method. Fifth one is, implement the simplified expression using the logic gates. Now these were the procedures for the design of the combinational circuits. Next is the introduction to the adders. Now before the study of the half adders or the full adders, we need to know what is an adder and what is the utility of adders. Now, digital computers and the calculators consist of arithmetic and the logic circuits, which contain logic gates and flip-flops that add, multiply, and also divide the binary numbers. These basic building blocks of a digital computers are adders. These circuits perform operations at speed less than 1 microsecond. So, these are the brief introduction of an adder. And the adders are mainly used in the calculators, digital computers, like this. Now let us move to the next slide, that is the half adders. This half adder is the simplest combinational circuit. This is the simplest circuit of an adder that performs the arithmetic addition of two binary digits in a half adder. So in a half adder, mainly there is the addition of two binary digits, or you can say addition of 1-bit numbers. There are two 1-bit numbers and we are adding them. So a half adder consists of 2 inputs and 2 outputs. Suppose 2 inputs are A and B and the 2 outputs will be sum and carry. So it is written here, 2 inputs are 2 1-bit numbers, and I had already told you that 2 inputs are 2 1-bit numbers. Suppose the first number we have taken A and the second number is B, and the 2 outputs are sum. Sum is for the sum is for capital S, we are taking capital S, and for carry we are taking capital C. So in a half adder we will be having 2 inputs and 2 outputs. 2 inputs are A and B and the 2 outputs are S and C. A and B are both 1-bit numbers. So on the whole we will be having 2 1-bit numbers and 2 outputs, that is sum and carry. The sum is denoted by S and the carry is denoted by C. Now this one is the truth table of the half adder. Now let us look at the truth table. Now see this one, this is the 2-bit combinations we have written. This is A is 1 bit, B is 1 bit, this one is the sum, output is sum, and this one is the carry. So 0 plus 0, you already know what is the sum, 0, and the carry is 0. One 0, the sum is 1 and the carry is 0. 0 1, the sum is 1, the carry is 0, and for 1 1, the sum is 0 and the carry is 1. Now the sum expression, or you can say the Boolean expression of sum, is A XOR of B, that is S is equal to A B bar plus of A bar B, and the carry is C is denoted as A AND of B, that is S is equal to A dot of B. Now this is a schematic of a 1-bit half adder where there are 2 inputs A and B and there are 2 outputs S and C. Now this is the logic realization, or the realization using the gates. A and B is, there is a XOR gate, we are getting the sum, and one where is coming from A and one where is coming from B, and it is going to a AND gate and we are getting a C. Now this is the simplest representation of a half adder. That is, a half adder will be consisting of one XOR gate and one AND gate. always remember this word. I'm saying that a half adder will consist of one XOR gate and one AND gate. One XOR gate and one AND gate. So let us move to the next slide. So this is the K-map simplification. Already here we have seen the expressions of sum and the carry. Now we will be finding the expressions using the K-map. Now for K-map, for carry, the K-map is two variable K-map. Now this is the K-map simplification. So as half adder, you already know there are two inputs. So there will be two variable K-map, that is A and B. For carry, this is 0, 0. For this is 0, 0, 0, 1. So we are doing the pairing 1. So this is carry is equal to AB, and here 1, 1 is present. So it will be sum is equal to A B bar plus of A bar B. So it is sum is equal to A XOR of B. So this one was the K-map simplification of carry and sum. Now this is the half adder using basic AND gates, OR gates, and the NOT gates. So just see here. Here we are having two inputs A and B, and this one is an inverter. This one is an inverter. These are the first AND gate, second AND gate, and the third AND gate, and this one is a OR gate. So from here we are getting A bar. Here we will be getting A bar, and from here we will be getting B. So this is A bar B. As it is going to AND gate means dot, so it is A bar B. Next here we are getting A, and from here we will be getting B bar. So it will be, as this is the output of AND gate, so it will be A dot B bar. So these two are going to a OR gate. S is equal to A bar B plus of A B bar. Next is A and B is going to a AND gate. So this is C is equal to A dot B. So we have got half adder using the AOI logic, that is the AND or and NOT logic. NOT is nothing but inverter logic. We can also call this as a AOI logic or AND or NOT logic. Now we are moving to the full adder. Now a half adder has only two inputs, and there is no provision to add a carry coming from the lower order bits where multi-bit addition is performed. For fulfilling this purpose, that is the disadvantage of a half adder. So for fulfilling the purpose, this purpose where we need multi-bit addition, the half adder is being designed. What happens in a half adder? Sorry, a full adder. A full adder is a combinational circuit that performs the arithmetic sum of three input bits and produces a sum output. Sum output is denoted by S, and the final carry is produced, that is C out. So normally what happens, a full adder has two inputs, and there is no provision for a carry coming from the lower order bits. That is, for multi-bit addition, half adder cannot be used. For multi-bit addition, we need to use a bigger adder. That is, the full adder is being designed for this purpose. And full adder consists of three input bits, and it produces two outputs, that is the sum output, that is the S or sum, or final sum, and the final carry or the carry, that is the C out. Next is, this is the block diagram of a full adder. Here we are having A, B, and this is the carry from the previous bit, that is C in. And these are the sum and the carry. Sum and carry. So these two are the outputs. So this is a truth table. The truth table, the inputs are A, B, and C in, and the outputs are carry and sum, that is C out and S. In case of 0, 0, 0, 0 plus 0 is 0. Again, 0 plus 0 is 0. So sum is 0 and carry is 0. 0 plus 0 is 0. 0 plus 1 is 1. The sum is 1 and the carry is 0. Next, this case, 0 plus 1 is 1 and 1 plus 0 is again 1. So the sum is 1, carry is 0. Next, 0, 1, 1. The carry is 1 and the sum is 0. 1, 0, 0. The carry is 0 and the sum is 1. 1, 0, 1, the carry is 1 and the sum is 0. 110, the carry is 1 and the sum is 0. 111, the carry is 1 and the sum is also 1. So this one was the truth table of the full adder. In the case of a full adder, as there are 3 inputs, that is A, B and C in, so it will be having 8 combinations. That is starting from 0 to 7. 0, 1, 2, 3, 4, 5, 6 and 7. And these are the outputs, that is Cout and sum. Next is using full adder, we will be doing the K-map. If we are doing the K-map of sum, see this one. This is A of A bar. This one is 0 and 1. So this is, if we do the pairing like this, we will be getting S is equal to A XOR of B XOR of C in. Next is for C in, if we do the pairing like this, we are just putting the ones here. In the case of the Cout, we are just putting the ones here. So if we do the K-map, we will be getting Cout will be equal to AB plus of BC in plus of C in A. Now this is very important. These 2 expressions are very important. Now we will be drawing the circuit. Now see, just look here. For having the general expression of full adder, we will be using the K-map method. To find the, we will be using the K-map method for finding the sum and the Cout for the general expression of the full adder. That is, the general expression means where there will be XOR gate and an OR gate. That is the general expression of a full adder. See, I am emphasizing on the word general expression. Whenever in your semester exam it is coming like this, that design a full adder, you can do it like this. That is, you can apply the K-map method and you can design the full adder like this. This logic circuit will be okay. But if you are told to design the full adder using 2 half adders, then this method is not right. This method will be shown in the later slides, how you will be doing the full adder using 2 half adders. Now look here, this is a general expression or to find the full adder. See, this expression was S is equal to A XOR of B XOR of C in, and this Cout was equal to AB plus of BC in plus of C in A. That is, in between them, in between this expression there is a AND gate and here there is a OR gate, and these are the XOR gates. So just look here, we are having 3 inputs A, B and C in. So this is A is going here and this is B is going here and C in is going here. This one is a XOR gate, so we are getting S here, that is a sum. Next, A is going, B is going, it is going as the inputs of an AND gate. Next is B and C in is going as the inputs of an AND gate, and A and C in is going as the inputs of an AND gate. These 3 are combined to go to the inputs of an OR gate. So in the OR gate, the output is Cout. So ultimately we are getting the Cout. So this is the logic diagram of a full adder or the general full adder, that is without using 2 half adders. When you will be told to just design full adder, you can do it like this. That is, you can write the truth table, then you can do the K-map of the sum and the Cout, and after that you can draw the logic diagram using the XOR gates and the OR gates. Next is the full adder using the half adders. This is very important. Now this is the truth table. Now let us look at the truth table. These are the inputs A, B, C in, and these are the outputs Cout and sum. So this is 0, 0, 0. So this sum is 0 and the Cout is 0. 0, 0, 1, the Cout is 0 and the sum is 1. And this 0, 1, 0, the Cout is 0 and the sum is 1. Next is 0, 1, 1, the Cout is 1 and the sum is 0. Next is 1, 0, 0, the carry is 0 and the sum is 1. Similarly 1, 0, 1, the carry is 1 and the sum is 0. Next case is 1, 1, 0, the carry is 1 and the sum is 0. Next is 1, 1, 1, the carry is 1 and the sum is also 1. Now let us see how we will be finding the expressions of the sum and the Cout. Just I've written the Boolean expressions like this. The terms where it is 1, 1, I've written the expressions. There are 4 ones, so there are 4 expressions. Like this, sum is equal to A bar B bar C in plus of A bar B C in bar plus A B bar C in bar plus A B C in. So from here, these two expressions I am taking A bar is common. So we are taking A bar common. From here, we will be getting B bar C in plus B C in bar. After that, from here, we are taking A common. From these two expressions, we are taking A as common. So we are getting B bar C in bar plus of B C in. Now this one is the expression of an A B X nor C. You know that when we are applying a inverter to a XOR gate, we are getting a XNOR gate. So we have written it like this. That is A bar. This one can be written as A XOR of B. This is nothing but the expression of XOR gate. That is B XOR of C in. So we have written A bar brackets B XOR of C in plus of B XOR of C in bar. So this has become A XOR of B XOR of C in. This is nothing but if you consider this one, just see here. If you consider this one as X, so this one will become A bar of X plus of A X bar. Like this. If you consider this one as X. If you consider this one as X, so it will be A bar of X plus of A X bar. So we can write it like this, that it is A XOR of B XOR of C in. So we have got the expression of the sum. That is S is equal to A XOR of B XOR of C in. Next is C out. Next also there are 4 ones here. That is this one, this one, this one and this one. A bar B C in plus of A B bar C in plus A B C in bar plus A B C in. From this two, we are taking from this two, this one. Just look here. This and this expression, we are taking AB as common. From here, we are taking AB as common. So we have taken AB as common. So it is C in bar plus of C in. And from this and this, we are taking C in as common. If we take C in as common, what we will be getting? That is, we are getting A bar B plus of A B bar. So ultimately, this one is equal to 1. That is C in bar plus C in will be equal to 1. So this one will become AB plus of C in into A XOR of B. So ultimately, the expression of C out is AB plus of C in into A XOR of B. So for designing a full adder using 2 half adders, we will be using this expressions that we have find out using the Boolean algebra. Now this is very important. You should always use the Boolean algebra method for finding the expressions in the case when you are designing full adder using 2 half adders. Now the logic circuit. Now this one is A XOR of B. It is going. Now this one is A XOR of B XOR of C in. This is sum. Now see this one. This one is C into of A XOR of B. This is going here. And this one is A dot B is coming from here. This is the expression like this. That is AB plus of C in A XOR of B. That is, this one is AB plus A XOR of B into C in. This is the expression of C out. Now look here. If I draw one line here and again one line here. Now this is one half adder. How it is half adder? The half adder means there will be one XOR gate and one AND gate. Similarly, half adder means one XOR gate and one AND gate. And these 2 half adders are being added using a OR gate. This one is one OR gate. So this is nothing but a full adder using 2 half adders. I hope you have understood this circuit. Here 2 XOR gates are used, 2 AND gates, and 1 OR gate is used. This is AB, this one is AB, this one is AB into C in into A XOR of B. A XOR of B is coming from here. C in is going. This is C in into A XOR of B. So this is plus. So this is nothing but A XOR of B into C in plus of AB. And this one is sum is A XOR of B. This one is coming from here, and C in is this one. So A XOR of B, XOR of C in. So this one was the half adder using two full adders. Next one is sometimes we need full adder expressions, that is the summation of mean terms, the expressions in terms of summation of mean terms, which we will be using in the later lectures when we will be designing multiplexers, decoders. Like this, we need the expressions of sum and carry in terms of summation of mean terms. So from here what we can see that this is the truth table of the full adder. This is the truth table of the full adder. So from the truth table we can see that these are the inputs, that is A, B, C in, and these are the outputs, C out and sum. So this is 0, 0, 0. This is sum is 0 and the C out is also 0. Next is 0, 0, 1. Sum is 1 and the C out is also 0. Next is 0, 1, 1. Sorry, 0, 1, 0. The C out is 0 and the sum is 1. Next is 0, 1, 1. The C out is 1 and the sum is 0. Next is 0, 1, 0, 0. The C out is 0 and the sum is 1. Next is 1, 0, 1. The C out is 1 and the sum is 0. Next is 1, 1, 0. So the C out is 1 and the sum is 0. Next is 1, 1, 1. Now, what is the meaning of summation of mean terms? Summation of mean terms means we will be writing the mean terms where the value is 1. That is this mean term, this mean term, this and this. This is nothing but mean term 1, this is mean term 2, mean term 4 and mean term 7. In case of C out, it is mean term 4, sorry, mean term 3, mean term 5, mean term 6 and mean term 7. So we have written summation of mean terms. S is equal to summation of mean terms 1, 2, 4 and 7. And C out is summation of mean terms 3, 5, 6 and 7. So this expressions using summation of mean terms is very important. Why it is very important? Because we need to make the implementations using the decoders, demultiplexers, multiplexer. This has got huge applications. We will see in the later lectures. In the case of the demultiplexer, we have to design demultiplexer using this sum and the C out. Similarly, you have to apply this sum and C out using a multiplexer. How to design all this? We can get it from this truth table. So this truth table is a very important thing for all of us. So before having the thank you slide, let us move here, because this is a very important circuit. You should remember each and every slide. This slide also it is also very important. Here, this is a half adder using full adder using two half adders, and this is very important. Why? Because already in the previous slide, in this slide, see, you have seen how to design a full adder using the general expression. That is, this is the general full adder, but this is not the general full adder. This is the full adder using two half adders. You have to design a full adder using two half adders. For this one, you have to find out the expressions using the Boolean algebra. In many of the books, these expressions are not given. Only the diagram is given. So please look in the lecture. This lecture is very important because in many of the books, on the reference book, you will not find this expression. This expression of C out. How to find the expression of C out? It's very easy. It's very easy because you have to just apply this once, and you have to just plus it, and you have to just apply some Boolean formulas, and after that you can find the C out. And this is also very important because this is nothing but one half adder, this is another half adder, and these two half adders are being connected using a OR gate. So this is the combination of two half adders for making a full adder. And this is also very important because this we are having applications in demultiplexer, multiplexer, decoder, etc. So thank you for listening to this lecture, and this full adder using two half adders and the general expressions is also very important for semester exam. So I hope the whole lecture was clear to all of you, and please study this lecture, and if you're having any problem, do contact me over the email, or you can also write some comments in the YouTube channel. Thank you.